This video explores how gradients, tangents, and constants reveal the universe's fundamental rules. By plotting observational data, we translate physical world into mathematical relationships, revealing quantities like acceleration, spring constant, Young's modulus, and the time constant. The important idea that ties these together is the straight line, y equals mx plus century. When data forms a linear relationship, the gradient m and the y-intercept c become direct measurements of physical reality. Since reality is rarely linear, you will need to use the tangent to find the instantaneous gradient. That is the gradient at that point on the graph. Zooming in reveals that the curve appears straight, allowing us to find the instantaneous gradient using a tangent line. This skill is used in many parts of the A-level course. When looking at motion graphs, be very careful to take note of the axes of the graph. If the displacement is plotted against time, the instantaneous velocity at any point is simply the gradient of the tangent line drawn to the displacement time curve. In this graph, velocity is plotted against time. The graph is a straight line. Comparing y equals mx plus c with the axes velocity v and time t, we can see that v equals at plus u. The gradient a is acceleration. The y-intercept u is initial velocity. When studying Hooke's law, we plot a force extension graph. The gradient k is the force constant of the object. When plotting a stress-strain graph's gradient E is the Young's modulus, the fundamental stiffness of the material itself. When looking at decay problems, such as a discharging capacitor, since the voltage drops exponentially, V equals V0 E/crossing. This does not easily compare with y equals mx plus c, and the tangent ploy does not help either. We cannot extract the time constant, CR, with a simple gradient. The solution to this problem is using the logarithmic straightener. This is the ultimate trick to unbend the exponential curve. By taking the natural logarithm of both sides, we force the exponential phenomena back into the realm of linear geometry. With the curve straightened to ln v equals -1/crossing t plus ln v0, the use of gradients works again. By calculating the gradient m of this new linear plot, we can extract the time constant, CR, as the gradient equals -1/CR. This table summarizes the use of gradients in A-level physics. Across the full specification, kinematics, materials, and electricity, the same mathematical methods using gradients and intercepts reveal solutions to many exam questions. This week, we will be practicing a variety of problems that use the idea of the gradient. In this way, we will cover a lot of the content of the course and hone one specific and really useful skill.